Hello, it's stat135, lecture 32. Last time we finished ANOVA, section 12.2, both parametric and non-parametric, and today we're starting regression. In particular, we're going to introduce matrix notation for multiple regression, the simple standard regression model for k is 1, and the geometric derivation of the regression coefficient. So for multiple regression. So for k predictors, we're going to show that it is where x is the design matrix. It's the transpose of x times x, quantity inverse x, y. So we'll see what all that means. So it's a bit inefficient to do simple linear regression and then do multiple linear regression. Since most of you have seen regression before, I'm going to do both simultaneously. So matrices are our friends. It allows us to efficiently write down formulas in regression. So we're going to use that. So y, the column vector y, is its n by 1 column vector, which is y is our response variable, and we have n observations. x0 is a column vector of 1s, and then I have k predictor variables. So x1 is my first predictor data. I have n observations, and so on up to xk. So from this data, I could make a scatter diagram, and our job is going to be to find the best fitting plane through that scatter diagram. But let's continue. So beta is going to be a k plus 1 by 1 matrix. So these are the true regression coefficients, and E, which is a column vector E1 to En, is our error terms. So let me emphasize that beta and E are unknown to us, and we can only estimate it. So X, which is called a design matrix, is an n by k plus 1 matrix consisting of the columns x0 out to xk, where n is greater than or equal to k plus 1. X is we require x to have full rank, meaning that these vectors x0 to xk are linearly independent, which means that the x transpose x is a k plus 1 by k plus 1 invertible matrix. Okay, the standard statistical model is that y is x beta plus e, where e is homoscedastic, so that means that the variance of these error terms don't depend on x. So I've just written out what my standard statistical model means in terms of the matrices, and so you can make sure that all the dimensions work out. And so this bottom thing here is saying that I'm writing my first observation my first response observation y1 as a linear combination of x11 to x1k with coefficients beta 0, beta 1 to beta k, and I have an error term, and so on. Do this for all observations. So here's the simple regression example of this. So I have k is 1, n is 3, and let's assume that there's a linear relationship between father's height and son's height. And so I have y is beta 0 plus beta 1x plus e, and I have three points, x1, y1, x2, y2, x3, y3, and I've drawn out the scatter diagram here. And so there are two lines to keep in mind. So there's Tyche's line. Tyche's line is the true relationship between x and y given by the standard statistical model. So, but I'll never know exactly what Tyche line is because I don't know what beta 0, beta 1 is. And hence I don't know what the error term E is. And then there's the regression line, which is what I observe. So I observe, we'll write down what the best fitting line is through our 3 points, and then we can say what the errors is, and the errors to the regression line is called residuals. So you're probably wondering who Tyche is. So Tyche is the goddess of fortune. Tyche knows what beta 0 and beta 1 are. Okay, and this is a old-fashioned Tyche. This is a modern-day Tyche. Those that go to Sin City in Las Vegas may have this image of her, but I'll let you choose your own image. So we're going to assume we have a linear relationship, and we're going to find the best fitting line called the regression line, and the residual is the difference between the observed value and the corresponding value on the regression line. And since the EIs are homoscedastic, the residuals should also be approximately homoscedastic. You should always plot the residuals. This is called the residual plot, and the vertical spread should be constant. So here I'm plotting along the x-axis the residuals that I have. So so I have the residuals for my n observations, and those are just numbers, so they have some natural ordering along the real number line. And what have I drawn here? Let me think. So actually, I think this should be, this is my y here. Yeah. Right. And so here I have my my xi's are along here. So like in this picture here, so in this picture here I have my xi's along the x, and I'm plotting so the residuals is the spread between the regression line and my observed value. So so if you just subtract the regression line from your observed value, you will get these EI hats, and the EI hats should look like there's just a common spread, so it shouldn't look like it's fanning out. That would be called heteroscedastic. Okay, so we want to minimize the sum of squares of the residual. So the sum of squares of the residual is actually the Euclidean norm of the residuals. So just to review what Euclidean norm is, if x is x1, x2, a vector point in the plane, then the Euclidean norm is the dot product of x with itself, or x transpose x. So it's x1 squared plus x2 squared. And more generally, if x is x1 xn, then Euclidean norm squared is the sum of the squares. So to find beta hat, our estimate of beta. There are two ways you can do it. You can do it with calculus, the method of least squares. You have a minimization problem. So you would be taking the derivative with respect to beta 0 to beta k, setting that equal to 0, and that's going to give you n simultaneous equations in k plus 1 variables with n greater than or equal to k plus 1, which you can solve. There's also a geometric solution. This is not in the book, but I prefer it because it's so easy. So the columns of X span a k plus 1 dimensional subspace since X has full rank. So you can visualize Y, which is a vector in Rn, as sort of sticking out of the column space. And right, so we want to find X beta hat that minimizes the residual. So the residual is that minimizes the Euclidean norm of the residual. So the Euclidean norm of the residual is the Euclidean norm of y minus x beta hat, and that is exactly going to be the orthogonal projection of y onto the column space. So we're looking for x beta hat that will minimize this distance, and so y minus x beta hat is the orthogonal projection, which means that the dot product of every column of x in your column space with the vector y minus x beta hat is 0. And notice that every point in the column space of x can be written this way. So the transpose of x dot y minus x beta hat is 0, and so that means that x, the transpose of x, y minus x transpose x beta hat is 0, and you can solve for beta hat as x transpose x inverse x transpose y, and so x transpose x inverse exists because x has full rank. In the special case when n is k plus 1, y lies in the column space of x, and so the norm is 0, which implies that y is x beta hat, which says that the residuals are 0 and the regression plane perfectly fits your data. So what is beta 0 hat, beta 1 hat for simple linear regression? We have this formula here, and we're going to see what that means when k is 1, and we'll show next time that beta 1 hat is the covariance of x and y over the variance of x, and beta 0 has the expectation of y minus beta 1 hat expectation of x. That's the show for today. More to come on Wednesday. See you later.